Welcome to another webinar. This webinar is the Advanced Well Control Volume 1. In this webinar we will have an introduction to well control simulations and modeling. And we will follow up with a webinar in a couple of weeks where we will talk more about our products and how our products can help you in well control simulations. My name is Morten Svendsen. I'm product manager in eDrilling, and together with me I have Rolv who is the CTO. Just one practical thing first. In the GoToWebinar application there is a question box where you can ask questions, and we will try to go through the questions in the end of the webinar. So then I will give the word to Rolv.
Good morning. My name is Rommetveit. Now you can see the contents of our webinar, our presentation today. First we'll give a background to the technology and the modeling. We will have today a focus on the physics of well control and well control modeling and how we can utilize this in simulations. In particular, the fundamentals of well control, transient influx, the effect of different influx types, gas migration in water-based mud and migration or not in oil-based mud, rapid flashing of dissolved gas represent a risk in oil-based mud. Also fracturing the well and the problem of having both kick and losses at the same time. We will have some focus on deep water well control, show an example of that. And finally we will summarize and list some well control risk elements which we will focus on in the next webinar. As a background to this webinar, here we can see the technology knowledge which is inherent in our company and in the personnel working here. And we've been involved in well control or the personnel since 1983 with a focus on gas kick development to understand, describe and model this. And there was also a specific focus on kick development in oil-based muds. Also the industry has of course had a high focus on this, and there were organized a number of joint industry projects to focus on and understand kick developments, and a lot of full-scale well experiments were performed. I mentioned some of these here. In 1989 there was a JIP to focus on kick developments in inclined and vertical well experiments, gas migration and control in these. In 1991 there was another JIP focus on the drilling of high pressure, high temperature wells, and field tests both in oil-based and water-based mud were performed in the North Sea with focus on well hydraulics, temperature development and pressure control. Extended reach wells were studied in large-scale kick experiments in a large-scale surface well or flow loop in 1995. In 1998 there was a JIP focusing on development of underbalance drilling and the multiplied hydraulics in these conditions, and experiments were performed in test well in Brazil as part of the joint industry project. Then 2001 there was another JIP focusing on well control and pressure control in deep water wells, and large-scale test experiments were performed focusing on hydraulics and gas migration. And the picture on this slide shows the rig where these experiments in Brazil were performed, and it was a water depth of 3,000 meters in this well. In addition, laboratory experiments have been performed up through the years to verify and sub-models and understand various processes. Experiments within gas migration and gas transport during drilling, PBT properties of gas and mud and the mixtures of these. And of course, in parallel with all this, well control and multi-phase drilling hydraulics modeling has been performed, and simulator development has been ongoing. And today, such simulators are now available and can harvest the results of all these R&D and experiments. It has been used for numerous well control studies also. I'll give a brief overview of the flow hydraulics model, which is utilized. This is an advanced transient single and two-phase hydraulics model, which is coupled to a transient two-dimensional temperature model. By means of this model, it's possible today to focus on the challenges in drilling, completion, well intervention and production operation related to hydraulics and well control. It's possible to perform integrated design of operations. This modeling has also been linked to advanced training simulators, and it's also integrated with real-time system, and it's possible to perform post-analysis. The model is designed to be very flexible, to be robust and fast, and can handle complex situations. In single phase, the transient flow and heat transfer model handles the sequences of different fluids, the density changes, the pump and rate changes and stops, transient temperature effects of all these. During drilling, it handles the flow of cuttings with slip. During tripping, it models the surge and swab, the compression, the acceleration, the elasticity of the drilling mud. And during pump startup, the breaking of the gels is taken care of. The fluid properties are modeled according to the pressure and temperature in the wellbore. When utilizing the model, it's also possible to calibrate the key parameters to match available data, like friction factors, rheology parameters, and heat transfer properties. So the governing equations comprise the conservation of mass of each fluid component and the conservation of the total momentum for the system. And a simplified set of these equations have been derived based on some assumptions. One of these is that all the flow variables depend on only one spatial dimension, the flow along the flow line. Second is that the temperature at the start of the simulation is known and depends also only on one spatial coordinate. The gas can be dissolved in oil, but not in water. And the fluid can in general be composed of up to 5 different components like drilling mud, formation gas, formation oil, formation water, and formation cuttings. The dynamic heat transfer model handles the heat transfer between the formation into the well and the drill string. The changes in the drilling fluid temperature may result in significant changes in the fluid density, in the active volume of the well, in the frictional pressure losses, and also it has impact on wellbore stability conditions in the wellbore. One important aspect related to well control is that temperature effects may cause other effects to be apparent when they are not present, and they can also cause temperature effects may be a reason to mask some important effects when these are present, so that you don't see important well control signs from the wellbore, for instance. The dynamic temperature is closely linked to the mass transport model, and there is a coupling between these, and it's called every computational time step, and it updates the temperature profile inside the running string and the annulus. Dynamic effects due to pump rate changes and string movements, both axial and rotational, are taken into account. Drilling will generate heat, and this is transported upwards. When the temperature model is activated, the temperature will be affected by the temperature gradient and the temperature of the pumped mud. In addition, friction in the drill string and friction between the drill string and casing will affect the calculations. So heat transfer takes into account the bottom hull assembly, drill string, casing and liner, the fluids and the formation. In a well-controlled situation, we model the reservoir with a dynamic reservoir influx model. The flow model simulates the interaction between the well and the reservoir, and during drilling the well is continuously extended according to the rate of penetration. When the drill bit penetrates into a porous reservoir, the difference between the wellbore pressure and the formation pressure will regulate if a flow from the reservoir of the formation fluids is initiated and a kick is started. If the pore pressure is higher than the well pressure, a flow will then start. The influx rate depends on the pressure difference between the wellbore and the formation, the length of the reservoir exposed to the wellbore, and the properties of the reservoir like permeability and porosity. If drilling continues, the reservoir length exposed to the well will increase, and this is used to simulate drilled kick. If a porous reservoir has been penetrated and then the well pressure falls below the pore or reservoir pressure, a kick will start due to the same process. But in this case, the reservoir length will not change since the drill bit is below the reservoir zone. This slide shows a picture of the important physical parameters which are taken into account and handled while modeling or simulating a complex well. But I can say also it's also taken into account in any well which is simulated. The mud composition is modeled in detail. It handles multiple fluids. The density is modeled as a function of pressure, temperature and fluid component. The same with rheology. The thermophysical properties of the system is modeled. The Cuttis transport with focus on the slip is handled, and the flow out of the model is handled. When we have a kick, the dynamic influx, as I mentioned, from the reservoir is handled. The gas can dissolve in the oil-based mud. We also can model loss to the formation. In the vertical part, the phase or PVT properties of the mixture is handled in detail, and also when we have free gas and drilling mud, the multiphase flow is modeled. There are some elements which are not part of the model which is used for evaluation, but they can be also added in specific studies like particle sagging, diffusion into the wellbore and hydrate formation. So to summarize, all this modeling makes it possible to handle the dynamic temperature effects, dynamic pressure effects, and the effects of transient drilling operations, and also the effects of various well-controlled methods. This summarizes some dynamic effects which are handled in the model. It handles compression and decompression of fluids versus pressure losses, fluid displacements, it moves fluids through the system. It handles the two phases, either liquid gas or liquid cuttings. It handles continuous change of operational parameters. The temperature profile is updated in the modeling. The model is coupled to topside when it deals with training, and this combined model is very complex for managed pressure drilling or dual gradient drilling. The density is a function of temperature, pressure and composition, and the same with rheology. Rheology is also a function of the flow velocity. And we utilize the three-parameter rheology model to model the rheology. Furthermore, on the phase properties, after an influx in a well, mixing will take place between the mud and the influx. And in general, hydrocarbon influxes can range from dry gas through volatile oil to condensate and heavy oil. Hydrocarbon gas solubility in the oil phase of the drilling is several orders of magnitude larger than in the water phase, and we assume that the solubility in the water is zero in the modeling. After an influx, the mixture conditions of the mud and influx will move towards thermodynamic equilibrium, and this condition will depend on the pressure and temperature in the wellbore. and some influx will dissolve in the mud when you have oil-based mud. And this will dissolve in the base oil. In general, the dissolution process is not instantaneous, but we assume it to be in the modeling. Now we will focus a little bit more on the difference between influx in oil-based mud and water-based mud. Dry gas influx is soluble in the base oil, and the bubble point of the mixture will govern where the flashing of the free gas will take place in the well. Gas or volatile oil in oil-based mud will have the following special characteristics. As long as the influx is dissolved, it will stay rather concentrated. The influx will not be distributed over a larger portion of the mud by slippage, and high gas peak can be expected when the gas reaches the surface. The expansion from such a system can be much more violent than from a gas-water-based mud system due to the combined effect of the large expansion and the violent flashing near the surface. The volume of gas influx changes when it goes into solution. In general, the volume of the gas influx will shrink when the gas molecules move from free to the dissolved states. This effect is reduced with increasing pressure. An influx of volatile oil in water-based mud will release free gas when it is pumped upwards in the well due to the pressure reduction, and the free gas will expand according to the real gas law. Influx of volatile oil in oil-based mud will mix totally with the base oil, and a new pseudo-base oil with different PVT properties than the volatile oil will be created, and the bubble point and volume of free gas released will then be different from that of the volatile oil alone. The expansion of gas in oil-based mud, as I mentioned, can be much more violent than that from a gas-water-based system due to the combined effect of large flashing, large expansion and violent flashing. And this picture here shows exactly a case where this or a similar incident happened on a well, and the gas came to the surface and it caught fire. The influx was not detected until it was too late.
Okay, so we will now we will run a simulation of influx in oil-based mud. So this is we are drilling the 8.5 section. I will just start the simulation when I talk. So we are drilling the 8.5 section. We have a water depth of 84 meters, and we are drilling into a reservoir and getting an influx. So now we are entering the reservoir, and you will see on the you can look at the pink line here that you are getting a larger flow return, and also as you see here we also model the pit gain and also the influx down here. So now we have shut in the well, and we are waiting to get a stable wellhead pressure before we start circulating the influx out. So in this simulation, we are going to do a driller's method. So we are going to circulate the influx out as long just as when this wellhead pressure is stable. So now we got an increase on our pressure, and both on the choke and on the standpipe pressure. We are not using a float in this string, so we get a reading for the pressure. So now we have started circulating the kick out. We can also show a plot here where we have the dissolved gas fraction in the well, and you can see that we are pumping it upwards. And you can see now we don't have any or very little free gas. It's mostly dissolved into the oil-based mud. Now we are pumping it out, and you can see we are keeping our bottom hole pressure constant, but also the the other pressures in the well. As soon we will be able to see the gas travel up in the annulus in the small drawing here on the side, so you can follow the position of the gas influx. So now we are moving upwards to the casing, and we can have a look again on the. So we have still it's all dissolved into the mud. Still. So to not spend too much time on the simulation, because we will show a couple of more things afterwards as well. So when the model calculates the kill mud weight itself, so when it starts circulating out, when the gas is out of the well, it will start pump the kill mud at the proper mud weight. Now you can see that when the gas is traveling past the casing shoe, you can also see the casing shoe pressure is dropping due to that you have the mud is then lighter because of the gas dissolved into the mud. So we don't see any flashing of gas out of the drilling mud yet, but it's traveling upwards. Yeah, so we have spent a lot of time now, so I think we will just go to the next slide, and we will show a bit more simulations afterwards with more details of for example, when the travel of the gas. So just go to the next slide.
Gas migration is very important during well control, and it's a key parameters. In general, the flow of mixtures of mud and hydrocarbons is a very complex and transient multi-phase flow process. And the free gas will travel either in the bubble or the slug flow regime. The so-called annular flow regime will only exist when you have a non-Newtonian drilling mud close to the surface, when you have a violent expansion. A lot of studies in experiments have been conducted to improve the understanding of the gas rise velocities and develop correlations in detail. And some of these have also been done under accurately controlled conditions in flow loops. Also, full-scale tests and experiments in vertical and inclined wells have been performed. One of the JIPs I mentioned is documented in SB paper 19561. And in this case, a total of 24 gas kick experiments were performed, and parameters varied, such as mud density, gas concentration, gas type, mud flow rate, injection depth, mud type, etc. And a lot of data was acquired and analyzed. And gas slip and migration was measured by 5 pressure and temperature sensors spaced out in the well. When does the transition between bubble and slug flow take place? It seems we have seen that there is a difference between Newtonian fluids and non-Newtonian fluids. The transition in Newtonian fluids is at approximately 25% gas, but in non-Newtonian fluids it is at less than 5%. So this is important to take into consideration when modeling, because the slug flow regime gives a higher gas slip velocity than the dispersed bubble regime. And the slip models have been correlated to the experiments, both small and large scale.
Okay, and then we will show the gas migration in a water-based mud. So this is, I will start this small video. As you see, we have already taken free gas into the well, and we are doing a flow check. So we are not doing anything. We are just standing still. And you can see the gas migrates upwards into the well because of its free gas. And I think we will just go, we will migrate all the way up to the choke line. So if we go to the next one, we have the gas migration in oil-based mud. This is the exact same well with the same parameters. The only difference is that we have an oil-based mud instead of a water-based mud. And as you see, we have the dissolved gas going into the gas going into solution, but you have some free gas because the fluid is kind of full of gas. So it's and the free gas is traveling upwards, but it goes into solution on the way up.
And the free gas comes into so-called virgin mud, which does not contain any gas on beforehand. So
now you see that all the gas is into in the solution, and it's not migrating anymore. So you actually have captured the gas into the fluid, and you have kind of a good control of what's happening there.
The well control model, which I've seen some examples of being used here, have utilized all these experimental results and the knowledge from theoretical research also. If you need more details regarding well control modeling, there is a long reference list in the SB book Advanced Drilling and Well Design, chapter 4.3. Regarding other well control risks, well, what we have done here so far is just to scratch the surface of well control and the risk related to that. There are a number of other issues which we have not dealt with, like the effect of gas dissolutions on the viscosity and cuttings carrying capacity, the settling on barite. We have not looked into the fracturing of the well, both combined kicks and losses, secondary kicks, and deep water well control is an issue which we will have a short look into in a minute. And challenges in deep water well control are pressure losses in long choke and kill lines. What happens if the gas passes the BOP and into the riser undetected? If you have gas migration or not in long risers, and if the gas is trapped in gelled muds. Also, there are a lot of challenges and risks related to dual gradient drilling, high pressure, high temperature wells, and also completion operations, because a number of kick incidents take place in completion operations.
So we're going to do another recorded simulation that we have done here. So what we are looking at here is that we are also in here drilling a 8.5-inch well. We have taken an Influx, and it's mostly dissolved gas. As you see here, it's a deep water well. So it's almost 1,000 meter deep water before the well. So now we are doing now we are starting to circulate the Influx upwards, and you can see it travels upward. This is edited a bit, so it's a bit quicker than it would be in a simulation. You can see it travels up here into the casing here, and you saw also when you passed the casing shoe, the pressure on the casing shoe also dropped. So what we will see now, when we get closer to the surface, it will start, you will see we get some more free gas before it's entering into the choke line. So what we saw here is that you had an increase in your choke pressure as the gas exited the well, and you saw the drop in the mud return, but you also saw down here that your gas exited the well. So now we have emptied the well for gas, and we have also, this is also driller's method, so here we also weight up and started pumping the heavy fluid, the kill mud. So you see a drop in your stamper pressure as we are pumping down the string, and here you saw that we the kill mud entered the well, and you saw that we then got a stable stamper pressure, but your choke pressure then started regulating to maintain a proper pressure. So, and we have another slide with just a screenshot. This is the same kind of well, but it's a water-based mud, and we have left, before we closed the well, we got gas up into the riser. So we have closed the well here, and open the choke line. So we see we'll start getting a choke pressure we are building up, but at the same time the gas in the riser is migrating and exiting the well. And here you see the rapid pit gain that we get due to the what's coming up into the riser, and here you also see the gas going out of the well. So then to the last slide.
Yeah, well, as I said previously, we have just scratched the surface related to well control risks. Some more risks here, for instance, the hydraulic limitations, the available drilling window to investigate that, the ECD, the swab pressures, the temperature effects, kick tolerances, depending on what type of kick you have. More on gas migration, the question of undetected kicks, especially dangerous in oil-based mud. Kill methods, what are the optimum kill method? And also the surface flow parameters, the limitation of the mud gas separator, can it handle the kick? And when do you expect gas at surface? How is the kick behaving in brine or water-based mud versus in oil-based mud? There's a lot of complexity when you drill high pressure, high temperature wells, and the well control is a key element in preparing for these wells. Deep water drilling we saw, and also in general wells with very narrow drilling windows. So some of these issues we will address in the next webinar. So thank you now for your attention, and we are open for some questions.
Yeah. So, but we are on our time, so maybe if you have some questions, you can just send an email to Rolv or me, and you will find our email on the edrilling.no webpage. So we know that your time is, we are all busy people, so, and we are over time already, so we would like to thank you all for joining the webinar.
Okay, thank you.